Today we will be discussing a different topic in chapter 7, which is 7.2, shear and moment equations and diagrams. This is actually a very interesting topic that discusses how the shear force, right, V, we named it V in section 7.1, or the bending moment M could change with distance. Now, remember that we had beams, and these beams had lengths, for example, 6 meters. Now, along the section or length of this beam, we had loadings. For example, we had distributed loadings, or point concentrated loads, or support reactions, and so on. So now, remember in the previous section we discussed, or the previous chapter, I guess, we discussed the method of sections. In the method of sections, we said that we take a section at any point along the length of the member, and we try and find the values for V and M. Now, but that was V and M at one single point across the length of the beam. But now, what if that was a beam, for example? What if we wanted to find how the shear force changes with distance across the length of the beam? Also, how the bending moment might change along the distance of the beam or along the length of the beam. So basically, we need to find equations that would relate V and distance x, which is length basically, right? Or portions of the length. So we need to find these equations, V related to x, as well as M related to x along the whole length of the beam. So now we don't only find one point for V or one value for V, we find infinite values for shear force V and bending moment. Now, as you probably might have noticed, I didn't mention anything regarding the normal force that we called N in the previous chapter. Simply because the book says that these beams are actually designed so that they can actually tolerate normal stresses. So normal stresses means shear forces or bending moment. So we will not be concerned with the value of N, or we will never actually calculate the value for N when we draw the when we find our shear and moment equations. And when we do that, we can now actually write or draw the shear force V as a function of distance. Also, we can draw the bending moment on the y-axis as a function of distance as the situation. So for example, look at this type of beam. Now this beam is called simply supported beam. Simply supported beam usually has two supports at these two ends. One support here, usually it's a pin support, and at the other end we have a roller, as we said, to allow for expansion and contraction with temperature change. So now guys, if you see here at this portion we have distributed loading, here we have concentrated load, and now here we have probably support reaction, or we actually do have support reaction. So now you see the nature of the loading changes with the length or the distance from this point to this point across the length. So now we can actually imagine that we have three different situations. Here we can have one situation here inside the distributed loading, one outside the distributed loading before the concentrated load, and the other one just right after the concentrated load. So we have three sections now, meaning that V has different values, or have different we can have three different equations relating V and the distance x. So eventually, when you draw your shear diagram, this is called shear diagram because it shows the dependence of distance on shear or shear stress or shear load, and here it shows this is called a bending moment diagram because it shows the bending moment versus the length or distance x. Now you can see that the shear force is actually changing with distance, and the behavior now changes with the position or the part or the section that we were working or the portion of the beam that we are working with. As you can see here, there's a linear relationship between V and X, where it's actually it's an inverse relationship. However, here we have a constant value for shear across this length. As you can see here, in this portion between A and B. So here, for example, we're talking about this portion. You see that there's no loading here. So basically, the shear force value should remain constant across this length. Then as you see, it will change. This behavior of V will definitely change now because we have a different loading. At point B, we have some external loading. So you see now it changes. We will learn how to draw these diagrams. Now, if you go to your book in the 14th edition and open to page 366 at problem 751. Actually, in your book, you'll see two simple examples. This is example, I guess, we check. So this is example 7.6. Example 7.6 is solved as well as 7.7. So I leave these for you because they are solved. So now we will go to the problems and I solve this problem for you. So this is problem 751, page 366. Now, in this problem is asking us to find the shear and bending moment diagrams for this beam. Now, the distances A and B are given as 2 and 4 meters. The loading P is given as 30 kilonewtons. So how do we think? How do we think to solve this problem? First, you have to find your support reactions. So find support reactions. So you take the whole beam, you replace these supports with their reactions, and then you find the reactions. Now, we know for a fact that at this support, the pin support, we have A in the Y direction, and we have A in the X direction. But you can be smart and say that AX, or the value of AX, should be 0, because the external load is actually going in the Y direction. So there's no loading to resist in the X direction. Hence, AX is immediately has a value of 0, so we don't care about AX. What about B? At B, here, we have also reaction in the Y direction only because it's a roller support. Now, you apply your equations of equilibrium. Definitely, we have two unknowns for the y-axis, so we go and use the moment equation. So just use it around or about any point A or B. So for instance, if you go and find it around point B or point A, it doesn't really matter. So this should give a value of 0 because this is equilibrium. So you have now By. So we're going about around point or about point A, it doesn't really matter. So this is going counterclockwise, so it should have a positive moment or create positive moment, and this distance is 6. Remember, A is 2 and B is 4, so this is 6. So this is By multiplied by 6. Now P is going clockwise and has a value of 30, so minus 30 multiplied by 2. This should give us a value of 0. So immediately By will be 10 kilonewtons. Since it's positive, then the direction that we assumed is correct. And now you go and use the this equation, summation of forces in the y direction is 0, right? So now you say that By minus 30, and we already know By is 10 anyways, plus Ay equals 0, and here this will yield a value for Ay of 20 kilonewtons. And that actually makes sense because 20 plus 10 is 30 and P is 30. So now we have equilibrium. So first, find support reactions and do that. And then point number 2, you have to decide which section to use or where to do sectioning. So this is the method of sections. As you can see, now whenever we have for example, some constant condition, for example here, we have some constant condition between, at this length, A. between 0 and 2 meters. So here you can take any section at this portion and you assume that whatever equations would yield definitely be valid for this distance between 0 and 2. However, you just take any section here. For example, if you take a section here, now here, this distance would be x. However, all these points will have values larger than x, but still these equations are valid for the whole length between 0 and 2. So make your sections or create your sections, whatever. Now, so this is the first section, which is basically between the point 0 and 2 meters. Why 2 meters? Now because we have loading here. That's why we stopped here. And then we will take the other one, another section, which is here, after the loading, at any point along this length after the loading, for example, say here. So now, the first section, I will just change the color. So the first section, now, here, so this distance is x. You just name it x, whatever you like. For this section, this first section, now, our equations that we would come up with equations. These equations apply for values of x larger than 0 and less or equal to 2. I would say equal, doesn't really matter. Now, if we go here, this distance now, we could also call it x. I mean, whatever you want to call it, it's up to you. This distance is x. And now, however, for this section, you take the whole beam. Don't take this section only. Be careful. Don't take this section only. Take the whole beam from the left up to the point where you decided to take your section. And now for this part, you say that all our equations apply for x values larger than 2 and less than 6. All right? Now here, it doesn't really matter where you put the equal signs. Actually, it doesn't really matter. However, you have to be attentive. That's true that our equations apply for these distances between 2 and 6. However, you have to take the whole part from point A up to the point where you made your section. My students actually sometimes make this mistake where they actually just take this part of the beam, which is definitely incorrect. So you have now two sections, one before the external load P and one just right after the external loading P. So now take your first section. This is the first section. So you said up to this point, whatever that point is. So you draw it. You draw your section. Right? So this is our section. Now we said that this distance is x. What do we have? We have our AY here. Right? So this is AY. And then we have, after we made our section, we have our shear force here, and we have our moment or bending moment going counterclockwise to assume or to give us a U-shaped beam, because in the convention we said that our bending moment should bend our beam upwards. All right, I guess that's it. This is everything that we need to know. Here we said that x, so let's just do this. So this is for x values larger than 0 and smaller than 2, this section. So now you apply your equations of equilibrium. First you say, for example, in this direction it's positive summation of forces in the y equals 0. So immediately you can see that V equals AY for equilibrium. So V equals AY equals 20 kilonewtons. And this is your first equation, which means that V is constant for values between 0 and 2 meters, and its value is 20. Now for moment, you take this direction is positive summation for moments about whatever this point. I mean, you can give it a name, you just can ignore it. This is 0. So here, as you can see, we would say that our moment anyways is going counterclockwise, so it's positive. Bending moment is positive minus, or anyways just go directly, this equals to AY multiplied by this distance, which is x, right? This distance, we don't know what that distance is. It's x. It's any distance between 0 and 2 meters. So this is 20 kilonewton meters. All right. So this is 20x, sorry. 20x kilonewton meters. This is equation 2. So we created our equations for V and M for distances between 0 and 2 meters. This is our first section. Now, go and take your second section. This is the second section, right? And this second section now is valid for values between 0 and up to this point. So this is x. This is x. Sorry. The beam should be taken between A and this point. However, the equations that we will come up with should only be valid for distances between 2 and 6 meters. Because this one was taken along this or across this part of the beam. We're done with this part between 0 and 2. Now we have to go and work with values between 2 and 6. However, we take the whole section from the left side of the beam. So we go and draw this part. So I'll just draw it in green. So this part should be up to the point that we decided we will work with. So now you remember we have AY here, right? So we have AY here at a distance of 2, we have P, which is 30 kilonewtons, right? And this distance, as you remember, we said this distance, the whole distance, is x. So if this whole distance is x and this distance up to point P is 2 meters, so this distance from here to here is basically x minus 2. So this is x minus 2. Right? Do we have anything else? Yes. We have our shear, which is V and M. And here, this portion, or these equations that would come up from this portion, would be valid for distances, as we said here, for distances larger than 2 and smaller than 6 meters. And now you just carry out. Sorry, I'm not really tidy. Anyways, I'm not tidy at all. So now you apply your equations of equilibrium just exactly as the situation here. So here in this direction, summation of forces in the y direction is 0. So you have AY is 20, right? We calculated AY is 20 minus P going downwards is 30 minus V equals 0. So now V will have a value of minus 10 kilonewtons. This is our third equation. You could actually assume a value of x of 1. It doesn't really matter anyways. This is our third equation. Minus 10 kilonewtons, meaning that the value for shear force is constant and equals to minus 10 for distances between x, or for distances of x between 2 and 6. Now, moment in this direction is positive, and this is actually should equal to 0. So you have your moment now here, right? It's going counterclockwise. And then you have this P about this point. You just always take it about this point. About this point, P, you remember P had a value of 30 and it's going counterclockwise, so it's plus 30 multiplied by the distance, which is x minus 2, right? And then we have minus AY. AY was 20, as you remember, multiplied by the distance, which is x. Okay, that's awkward now. Multiplied by x. And this is 0. So if you solve for M would be, or M would equal to 60 minus 10 x. This is our fourth equation. That's it. We're done. Now we go and plug our equations into, or plug the values that we get from the equations into diagrams. Now I'll just move this one here so you can actually use it to draw our diagram, or our diagrams actually. Now, so this is V in newtons or kilonewtons, I assume kilonewtons. And this is x, or length, whatever, x in meters. So here we have 2 meters, right? Remember, this is 2 meters. And this is 4. So, as you actually know from our first equation, here, it says that V has a constant value of 20 for x values ranging between 0 and 2. So it's 20. Between 0 and 2, let's assume this is 20, for example. So this is 20. So it should be constant up to this point. Just draw a line. Okay? 20. Now, what about the other equation? The other equation, number 3, it says for values between 2 and 6, V would have a value of minus 10. So immediately now, so if you assume this is minus 10, so it would go down to this point. I'll just I don't know how to remove this anyways. So this value of minus 10 is constant all the way up to 4 meters. So this is your diagram now. Okay, this is your shear diagram. Now what about bending diagram, or bending moment? Sorry, for bending moment now, just do exactly the same thing. Use the equations to draw. Let's see. Actually, I don't know if it has negative value. So this is M in kilonewtons meters, and this is X in meters. This is 2 meters. I'm not going to write that down. Probably I will. It's fine. 2, and this is 4. So now we go to the first equation, to the first section. Sorry, we see that X have our moment is a function of X. It has a value of 20x. So, but this is linear. So assume that x is 0. So this is valid between values of x between 0 and 2. So assume x is 0, so it will have a value of 0 at 0. So at 0 it's 0. What about 2? Remember, it's 20x, right? It's 20x. At 2 it has a value of 40. 20 multiplied by 2, this is 40. So this is 40 kilonewton meters. And since it's a linear, the equation is linear actually, or the dependence is linear, whatever that is. Okay, now we're done for distances between 0 and 2. What about distances between 2 and 6? We go to this equation. So let's apply, for example, the first one, the first boundary, which is 2. So 60 minus 10 multiplied by 2 at 2. 60 minus 20, this is 40, which is exactly 40 kilonewton meters, which is exactly the same point, 40 at 2. Okay, now again, the equation is linear, so we actually need only 2 points. What about the other point, which is at x of 6? So at 6, we have 60 minus 10 multiplied by 6, and this is 0 kilonewton meters. So now it would go here to 0. So you see, now our diagram would look like this. Okay? Meaning that the moment changes with distance. And now a very important point that we will be discussing later is that at this exact point where the shear force equals to 0, here we will have a maximum moment value, or the maximum value for moment. So M is maximum whenever shear equals 0. We will be using that in a different section later, probably in section 7.3. So that's it. This is how we draw our shear diagram and bending moment diagram. Thank you very much. In the next video, I'll be discussing another problem, also a very simple one. Thank you.